the science behind polymerization. Alright, so now we're going to be looking at how we actually make the polymers from the monomers. There's two main types of polymerization. The first one is addition, the second is condensation. And we're going to be focusing on this portion here in this video. But let's define what polymerization is. So polymerization is when you add monomers together to make long chains of polymers. So let's have a look at that. Now with addition polymerization, the characteristic feature of this is that you're breaking a double bond. And when you break that double bond, you're adding something to it. That's the big difference. We're adding something to the double bond. That is the feature that you have to memorize with addition polymerization. With condensation, we're breaking a double bond. The feature here is you're actually removing a small molecule. We're removing a small molecule from the actual monomers to join them together. Okay? So let's have a look at polymerization here. The first one here with addition polymerization is the formation of polyethylene. That's the one we're going to be looking at in a lot of detail. We have previously looked at this concept, but we're going to re-examine it. That's where we got up to. In this video, we're going to be looking at the two different types of polyethylene that are made. Now, the other addition polymers, which we're not going to get into in this video, but in the next one, are things such as the one that makes that polymer. What's the name of the monomer? Can you recall that? What's the common name of the monomer that makes PVC? Good. I hope you said vinyl chloride. Then we have the other polymer, polystyrene. What is the monomer that makes polystyrene? Yeah, styrene. Now, if I was to ask you this is a bit of a revision session, isn't it? If I was to ask you the systematic name of those, could you do that? What's the systematic name of ethylene? Ethene, good. Systematic name of vinyl chloride? Chloroethene. Systematic name of styrene? Ethinyl benzene. So that's addition polymerization. Some examples of condensation polymerization, where we're taking a small molecule out to join two monomers together, would be the formation of cellulose, the formation of starch, so they're both plant-based. Then we have glycogen. Now what's glycogen? Well, glycogen is the stores that we have in our liver. We join unused sugar molecules, glucose molecules together when we eat, and that stores up in the liver, and then that's our short-term energy supply. So those PE heads who study PE or biology should know this term glycogen here. So that's an animal process in animals. Then I guess we could talk about the formation of proteins by joining amino acids up. Right, so we can say the basics behind the primary structure of proteins by making amino acids. DNA. All of these things are made by condensation polymerization. We could even add plastic. So if you're drinking a bottle, then we can have PET bottles, polyethylene terephthalate. We can also have things such as nylon. So there's lots of condensation polymerizations there. We're not going to look at those in detail. We're going to do one or two of them briefly. We'll re-examine some of those, especially proteins, cellulose and starch, in a lot more detail when we do an option topic. So this is addition polymerization. Let's look at it in more detail and look at the two different types and how they're made. Alright, the first one is looking at low density polyethylene. So when we make polyethylene, there's two main types. There's low density polyethylene and high density polyethylene. So low density polyethylene is characterized by a structure that has lots of branches in it. And because it's got lots of branches, it takes up a lot of volume, and so therefore its density is lower. And here are some pictures of some objects that you might be familiar with that are made by low density polyethylene. The characteristic feature of this is that it occurs at high pressures, 100 to 300 megapascals, and about 300 degrees Celsius. Now the polymerization reaction. Well, what is a polymerization reaction? It's when you join monomers together to make long chains of monomers called polymers. So in this process here, we're going to be using something called a free radical polymerization. Okay, so let's write that here. Free radical polymerization. Well, we know addition polymerization is the adding of a substance to a double bond, but this free radical. So free radicals are molecules that have an unpaired electron and therefore are very reactive. Okay, so let's think of something that you might be familiar of. H2O2, hydrogen peroxide. If I was to draw that, there would be HOOH. That's the structure there. So the key functional group is this OO bond here, the oxygen bond. And I'm so tempted to go like that, draw some hair and a face. Alright, just needed to do that. So this is called a peroxide, and we're going to make a free radical peroxide, but we're not going to be using hydrogen peroxide, we're going to be using something called benzoyl peroxide. As you can tell probably from the beginning of the name here, benz, it contains a benzene ring. So let's draw it, and I'll show you how it makes a peroxide. So that's the structure of benzoyl peroxide. It's got a benzene ring. Here is our two oxygens, which is the characteristic feature of a peroxide. So that's called benzoyl peroxide. Now, how do we make it into a free radical to start this process? Well, we use light. So let's just talk about the steps now to make low density polyethylene. So if we do step 1, the first name is called initiation. And initiation is making these free radicals from our peroxide catalyst. So let's just draw it here. So we've got our peroxide catalyst. Now, how do we make this? Well, we use a light, such as laser, to activate and stimulate the electrons in this bond here, right? So we're going to put light here. Now, being a physicist, we could just write HF, right, which is the energy of a photon of light, right? You'll learn that if you do Year 12 physics. But that HF is just equal to the energy, right? Have to mix the two together, right? So we have a bit of light going in there like a laser. That causes the electrons to break homolytically, all right? So homo is the prefix meaning the same, lytic means to lysis. So we're breaking it evenly, and so one electron goes to that side, one electron from the bond goes to that side. And so we end up with a free radical. There's our free radical. I've placed a little dot there to represent that it's a radical. I'm purposely ignoring all the other valence electrons. Remember, oxygen's got 6, so one valence electron's in this covalent bond, one is in there, so it's got 4 remaining. So I could put the 4 like this, but I want to really emphasize that it's a radical, so let's just get rid of those just for the moment. Right? I want to get rid of them because I really just want to emphasize that this is a radical. Make it simple at the moment. So that's initiation. Initiation, the first step is the creation. We're going to look at the step 2 now and see what this radical does. Okay, so rub this off and we'll get step 2 happening. The second step is called activation. And activation is when that radical reacts with the first ethylene monomer. Alright, so it reacts with the ethylene monomer to actually make an ethylene radical. Okay, so if we have our peroxide catalyst here, or I should say the peroxide radical, there it is, then we have ethylene, then that electron attacks the double bond there, and we have the first breaking of the double bond, and that creates, and I'll just draw it over here, another radical. Okay, so there's our next radical. So that's called activation. Step 3 is propagation. Step 3 is propagation, and that just like when we did thermal cracking, if you remember, thermal cracking had steps. First one was initiation, then it was propagation, and then termination. So this has got an extra step in it, but the meanings are basically the same. Initiation to get the process started. In thermal cracking, it was increasing the temperature, and that caused kinetic energy to break the bonds. In here, initiation is actually starting the process by creating a peroxide radical. Propagation was to make more of, to make the process longer. Well, in this instance here, we're growing the chain. Okay, so this is where we get this radical reacting with more ethylene molecules to grow the chain. And it just keeps going, right? So the chain's getting longer and longer and longer. Okay. Step 3 is termination. It's exactly the same, where we get two radicals joining together to neutralize. But before we look at termination, which is a very simple process, let's talk about this backbiting. Okay. So remember before when I drew low density polyethylene, I said it was a chain, so it was a branched structure, and if it's branched it takes up more space, and if it takes up more space or volume it has a lower density. So we've talked about growing a chain here along here, but what about this side branches? Well, as this propagation happens, every now and then this growing chain turns back and reacts with a part of the other chain, part of the beginning part of the chain, to create side branches. And this backbiting occurs randomly, and all you need to say is that branches are caused by backbiting of the main chain during propagation. You don't need to be able to draw how that happens, right? So that is what causes the property of low density polyethylene to have a low density, is these chains, right? This backbiting. So step 4 and termination is when you get your two radicals combining together to neutralize the process. To neutralize propagation. Okay, so that's low density polyethylene, and they're the main steps that you need to know, and you should be able to be able to draw reactions for it. Okay, in your answers. In HSC level or more sophisticated levels of chemistry, you need to be able to illustrate your points by having reactions, not just naming the steps, but naming them, describing them, elaborating them with chemical equations. So that is low density polyethylene. Let's now have a look at high density polyethylene. As the name implies, it's got a high density, and that's because the chains are more linear. They can pack closer, there's less branching. And we're going to look in the next video about the properties resulting from this difference in bonding. But you can see from the pictures there that there's some of the things that you may be aware of that are made of high density polyethylene. Having a higher density means that they're stronger, they're more rigid, they're more opaque, right? So let's have a look very briefly. You don't have to go into much detail when we talk about high density polyethylene, but the purpose here is that we want to prevent backbiting. Okay, it was the backbiting that caused a lot of the side branches, so we want a process now that prevents a lot of backbiting and therefore predominantly gets longer chains. And we do that by using two main processes, and you don't need to remember formulas, you just have to remember the names. Okay, the first thing is that we can have a Ziegler-Natta catalyst. So a Ziegler-Natta catalyst, that's just after the people who put forward, who discovered this process. Right, now textbook goes into a lot more detail about the structure. Don't need to memorize the structure, just the name. So the Ziegler-Natta catalyst, and all you have to say, it allows ethylene molecules to combine in a linear fashion, which prevents backbiting and therefore prevents branching. And the same sort of thing happens here with metallocene catalysts as well. Okay, so metallocene catalysts is just using a different molecule with two benzene rings that hold it together like a little sandwich and allows it to form in straight linear chains. So the main thing here, and this doesn't get tested very often because the details are a little bit too complex to get into, whereas low density polyethylene they do test in more detail. But with this here, the main thing they want you to understand here is that high density polyethylene is because of the chains are more linear and less backbiting and branching, and that's because of the use of catalysts, specifically a Ziegler-Natta catalyst or a metallocene catalyst, and that allows straighter chains to be produced and therefore a different type of plastic. Okay, so that's it for addition polymerization. In the next video we're going to be looking at the properties of the two different plastics and relate that to bonding. And also we're going to maybe talk a bit about other addition polymers such as such as polyvinyl chloride and polystyrene, and relate that to bonding and structure, properties and uses. Okay, that's it. All right, make sure you got it all down, and I'll see you next time.